And the first one will be by Floriane Leclercq, whom I had the pleasure to go skiing with in Utah a few years ago. And she's from Geneva, working at Geneva, and will tell us about the cold interstellar medium, circum-galactic medium, at high redshift observed in Lyman alpha. You already, I think, yes, you already shared your screen. So, it's now time.
Okay.
Please start.
So yeah, so first of all, I would like to thank the organizer for allowing me to give this talk. And yeah, so I'm a postdoc at the University of Geneva, and I'm also working within the MUSE collaboration. And so today I want to tell you about, yes, the cold ISM and CGM of distant galaxies observed in Lyman alpha. So just a bit of introduction, talk about the circum-galactic medium. So why do we care about it? Because this is really where we expect the gas exchanges between the galaxy and its environment to take place. And those gas exchanges are really regulating the star formation. So if we want to know more about the galaxy evolution, we need to observe this circumgalactic medium, and to map it, it's quite difficult because of the low surface brightness of it. And so to map the cold CGM, we can use the Lyman alpha line, which is the brightest line, recombination line of the hydrogen atom. And it's also a resonant line, meaning that it scatters and illuminates the H1 cloud. And here on the left, you can see those Lyman alpha extended emissions, so scattering into the CGM at low redshift in blue. And at high redshift, we can see also those big and bright nebula, Lyman alpha nebula and blobs around the quasar and massive galaxies, but of course, they are not representative of the bulk of the galaxy populations. So what we would like to do is observe the cold ISM CGM for low mass galaxies. And for that, we need sensitive instruments. And this is what we are trying to do with the MUSE, which is an IFU. And all the results I'm going to present you here are based on data from the MUSE Deep GTO program, targeting the MUSE Hubble Ultra Deep Field. And so those MUSE data are 10 to 30 hours deep, and it is a mosaic of 3 by 3 MUSE fields. And here you see the redshift distributions, and you can see that at higher redshift higher than 3, we see only Lyman alpha emitters, and we have actually about 800 of Lyman alpha emitters. And so around those objects, we try to detect extended Lyman alpha emission to trace and characterize the cold circumgalactic medium. And actually, we did found quite a lot, so more than 140 Lyman alpha halos. And here, I don't want to give you too much details about the spatial analysis of the Lyman alpha halos. I just want to say that they appear to be ubiquitous around galaxies at redshift higher than 3, which underline the fact that the CGM has a rich cold gas content at high redshift. And those halos extend over tens of kiloparsec. They are also, their properties do not evolve much between 3 and 6, and they appear quite diverse. And also, it's quite difficult to link the properties of those Lyman alpha halos with the UV properties of the host galaxy. So linking ISM and CGM properties is quite difficult with Lyman alpha. So what about the spectral properties now? So as I told you, the Lyman alpha special Lyman alpha emission looks quite diverse, but also the Lyman alpha lines look quite diverse in shape. And so our new study, let's say, is to study the spectral properties of those Lyman alpha halos. So we start from this parent sample of the halos we have from MUSE, and for the 6 brightest ones, we were able to carry out a resolved analysis. And for the others, we just tried a 3D decomposition of the ISM and CGM contribution of the Lyman alpha. So here you can see the distribution in properties of our sample. So with this selection, we are selected the brightest galaxies in UV and in Lyman alpha, but still those are quite low mass galaxies, so 10 to the 9 solar masses on average. And so here I'm starting with the resolved analysis of those halos. So on the left, you can see the HST image, so tracing the UV continuum of this galaxy, for instance. And here, this is the corresponding Lyman alpha narrowband image. And what we've done is we perform Voronoi binning. So in the solid contour shows the area studied for this resolved analysis. So this is only the inner part of the Lyman alpha halos. So it's in 15 kiloparsecs. And we fit the Lyman alpha line in all the different bins. And this is what, so we got some map. So here I'm showing the map of the peak shift of the Lyman alpha line relative to the line in the center, because we don't have the systemic redshift for those galaxies. We only have Lyman alpha line, which is a resonant line, so which doesn't trace the systemic redshift. And here, this is a map of the width of the line. And here I'm showing some lines extracted in the center in orange and in the different region of the CGM in blue. So yeah, in the center, we can say that it's the ISM, but it's not resolved in this case. Okay, so as I told you, there is six objects like this. So here I'm showing 2 more. And what we can see is that there are variations in the Lyman alpha line shape. Those variations in the peak position, for instance, are quite small, so lower than 200 kilometers per second, but still significant. They are a bit larger in terms of width of the line because they go up to 500 kilometers per second. And we see that the lines varies between the ISM part in here and the CGM part, but also within the CGM itself. For instance, here the lines are different and here also. So it means that it suggests that we have a complex and diverse configuration of the H1 distributions for those galaxies. What we can tell also is that we do not observe an obvious velocity fields, except maybe for these objects here, and also maybe this one. And this would suggest that we have CGM scale bulk rotations. And I refer to Smith et al. 2019 for this, because it observes this in simulation as well. And also, in all the bins, we have single peak Lyman alpha lines, except for this object, in this bin, where we have a kind of blue bump, which would suggest that there is an infalling gas here, so which is interesting as well. Okay, so this is for the resolved analysis of those Lyman alpha halos. And now I want to talk about this 3D decomposition of the Lyman alpha halos. So for this, we were able to increase the sample, but we have to ask a simpler question, which is, are the Lyman alpha lines emerging from the ISM and the CGM the same? Are they different? So I won't go too much into the details about the decomposition, but it's 3D 2 components models, and which enable us to really disentangle the line from the ISM, emerging from the ISM and from the CGM. And yeah, so with this sample of 19 objects, we were kind of able to carry out a statistical study. Okay, so if we look at the distribution of the full width of maximum in the core or ISM in orange and in the halo CGM in blue, we can see that the lines appear to be in median. So if we look at the vertical lines, broader in the CGM, and also redder. So this configuration is expected if the Lyman alpha photons are emitted in the ISM and then scattered into the CGM, according relative transfer models, and it could maybe tell us a bit about the origin of those Lyman alpha halo, the powering mechanisms. Now, if we look on a galaxy by galaxy basis, so we look at the ratio between the two for each galaxy, and the peak separation between the two lines in the ISM and the CGM, we see that those distributions are quite have a large dispersions, quite wide. And so this indicates that we, again, meet different configurations for the called ISM+CGM traced by Lyman alpha. For instance, the line can be narrower in the halo than in the core, but also bluer. So we really find a large diversity. And now that we have those parameters, we looked for correlations. So one of the correlation we found, so we found only two, but one of them is this one. So the peak separations, the peak shift of the Lyman alpha line in the halo compared to the width of the halo, and we see that.
So that's 2 minutes left.
It correlates, and this trend is also observed in integrated spectra. So this is a paper by Vera Metal 2018, and they also, this is quite well explained by expanding wind models, meaning that, again, the photon would be emitted in the center of the galaxy and then scatter in outflowing media. And which is interesting here is that we actually also see this trend locally in the galaxy. So this would mean that we are really seeing outflowing gas at different scale. And also, as we saw earlier, with variation in the H1 column density, so could be maybe some clumpy outflows that we cannot resolve the clumps with the MUSE data. Okay, the other correlation that we found is the width of the lines, both in the ISM and CGM, with the beta slope. So meaning that the radio galaxies show a broader Lyman alpha lines, both in the ISM and CGM, meaning that maybe the more evolved galaxies will show broader lines. So this was the second correlation, and we didn't find any other correlation. And also, as I showed you, we found a large diversity of the Lyman alpha lines. So meaning that to really understand this connection between ISM and CGM, at least with Lyman alpha, because we need to decode the line, we really need models and simulations. And this is actually an effort which is ongoing. So here I'm citing some studies, some recent studies. And also to decode this line for those high redshift objects, we need the systemic redshifts to better characterize kinematics, for instance. And this would be possible with, for instance, James Webb Space Telescope or other instruments. And also, if we go deeper in the data, maybe we can detect other lines like C3. And this is what we are investigating in the MUSE extremely deep field, which is 140 hours deep. And also, yeah, we would like to have better spatial resolutions to resolve the ISM. And the lensing can greatly help here. And I'm referring to this paper where we study two Lyman alpha halos, so lensed Lyman alpha halos. And also we can use adaptive optics with MUSE. And this is my summary slide. So I just presented you the first analysis, statistical analysis of the spatially resolved spectral properties of the Lyman alpha halos around the high redshift galaxies. And the main conclusion is that we maybe these studies suggest that we are seeing outflows at the ISM and CGM scales. And it also underlines that it's difficult to connect the cold ISM and CGM, at least with Lyman alpha. And that we will need model simulations or maybe the help of lensing to improve our understanding. And thank you.
Thanks a lot. Thanks a lot. That is excellent. Almost on time, and we have plenty of questions. I think we have time to answer one of these. I will let me just see here. I'll take the first one by Ilseng Yun, who's asking if these Lyman alpha emitters are in overdense regions, so like protogalaxies.
No, so the UDF is quite is not an overdense region, so I would say no. And we also have, we are finding Lyman alpha halos from redshift 3 to 6, and they are quite well distributed. So I would say no.
Okay. I guess there's time for a quick question. So you define how do you define the border between the galaxy and the halo? When you say 65% of the flux is in the halo, how do you observationally define what is halo and what is galaxy?
So we are fitting so the UV scale length is fitted on the HST data, this HST image, so without Lyman alpha. And we are using this scale length, we fix this scale length, and then we use our two components model where the scale length of the first component is fixed to this HST UV image. And this is what we call our core or ISM component.
Cool. Okay, thanks a lot. There are more questions for you to answer in the chat. But let's move on to the next speaker.